In this video we're looking at assembly language, and this is 4.2 in the CIE 9618 spec. So assembly language is a low-level programming language as opposed to things like Python, which are high level. A low-level language is very close to the hardware. Assembly language consists mainly of mnemonics. A mnemonic is something that's easy for humans to remember, or makes something easy for humans to remember. Now, machine code is just numbers. It's binary coded numbers that the machine uses, and that's difficult for humans to remember. So it's replaced in assembly language with mnemonics. So it's a short code that's easier to remember. There's a one-to-one relationship between the mnemonics and the machine code. So for example, if you are adding two numbers together, if you're adding a number and the contents of the accumulator, you might have a machine code instruction like that. It looks like a longish binary number, a 16-bit binary number there. That's quite difficult to remember, so it's easier to remember a mnemonic like add instead. So assembly language basically just replaced machine code instructions with mnemonics. It's worth noting that machine code instructions are made of two main parts, at least in our simple view of the world. So an opcode and an operand make up an instruction. The opcode is a unique number that represents a particular operation, such as an add. Now all the opcodes together create what's called an instruction set, and the instruction set is everything that the CPU can actually do. Every operation, every instruction that it can do is in the instruction set, no more, no less. You can't do anything that's not in the instruction set. And every single one of those instructions has a unique binary number which represents what that is that it needs to do. The operand is data that may be required for the operation. For example, if you are adding a number to the contents of the accumulator, you need to know what the number is. So the operand tells the CPU what that value is or where to get that value. So it knows what to do from the opcode and what to do it with an operand. So an instruction, sometimes you refer to these things as a word. A word is basically a unit of size. It's the size of instructions, the size of a bus, and so on. So don't worry about too much about the meaning of the word. It's just a sort of unit of size. So we've got the opcode on the left there. That's what we need to perform. For example, loading something into the accumulator. And operand on the right, the value that it needs to do it with. So in this case, we're doing it to what says there #5, which means actually literally the value 5. Okay. So we've got opcode and operand. Opcode is what you need to do, and operand is the data or address you need to use. In CIE, we have various categories. They list 5, but then go on to have bit manipulation as well in section 4.3. That's the next section. So we've put them all here, all 6 of them. These are the separations of the different kind of instructions. And whilst they give you the whole tables in the exams, you don't have to remember the individual instructions. You may have to remember the categories of instructions as they're given here. So the first one, data movement. The loading things into memory, loading things into the accumulator, moving them around from place to place and storing things back into memory. Those are all part of the data movement instructions. Then we've got arithmetic instructions, the add, subtract, increments and decrements. They're all arithmetic. You've got unconditional and conditional instructions. These are for the flow of execution. We've got a jump. Jump is always jump regardless. And then we've got jump if equal and jump if negative. And in order to do jumps, the jump equals, the jump negatives, you need to know what happened when comparing things. So then we've got a section for comparing instructions, and in CAE they have CMP compare, which is a value that you're given, like an immediate value, and then you've got a CMI indirect, comparing with the contents of an address. Then we've got a group for input and output, in, out, and end. Actually, the end in that section just halts the program. So input output would be in and out. And then the bit manipulation instructions that we'll look at more in section 4.3. So breaking down these instructions they give you, these are all in the spec, the 9618 spec, and of course your exam board may have different instructions, use a different one, but they're very similar in the sort of things they do. So LDM, this is using an immediate addressing mode, which means that the operand actually contains the value you need immediately. You don't need to go and look for it anywhere. And in this case, we're using hash to indicate the type of number that we have in the operand. You can do denary numbers, you can do binary numbers, and you do hex numbers. In this case, CAE use hash to indicate a denary number. So if it was 5, it means denary 5, not hex 5, for example. Whatever it is, you can say which one you want with the symbol hash B for binary and ampersand for hex. And then we've got a load direct. So direct addressing, in this case, we're loading the contents of the address that we had in the operand. So we're given the address, we have to go off and look at it, and then we can put that value into the accumulator. And then we've got load indirect. So the address that we're given in the operand is used to point to another address, and then that address tells us where to find the contents that we move into the accumulator. So it's indirect. We have to do a couple of jumps before we get to it. So let's just recap that. Immediate ones is already there in the operand. You don't need to go anywhere. Direct, you have to go to one jump. You have to jump to an address to find the content. And then indirect, you have to do 2 jumps. You have to jump to that address, and then that gives you an address, and you jump to that address, and that gives you the value. And then we've got LDX, which is indexed addressing. So we add the contents of the IX register, the index register, to whatever address we're given in the operand. That gives us a new address, and that address is used to go and locate the value. And then we've got LDR. This is immediate addressing. So we load the number n into the IX in this case. So we don't put it into the accumulator, we put it into the IX. Then move, you would have a symbolic representation of a register. So for example, that could be ACC or IX. And you move the contents of the accumulator into whatever register you're told within the operand. And then same sort of thing for store. You store an address, and you store the contents of the address. The contents of the accumulator at whatever address you're given. And if you come to arithmetic operations, we've got the add, sub, inc, and dec. Again, CAE use slightly different formats depending on what mode we're using, what kind of thing we're doing with it. So the first one there is add, and then address, you're just given the address. So you add the contents of the given address to the accumulator. So we jump to that and we get it. You can do like a immediate add as well. So there's 2 types of add here, basically, depending on the syntax. The add with a hash n or bn or ampersand n means just add that value in the operand directly to the accumulator. Similarly for sub, they've got 2 types. You can sub with an address, means you just go get the value from that address and subtract it from the accumulator. And then obviously the result comes back into the accumulator. or a sub, and you actually give the value as an immediate value. You've got inc, which increments a register, so you can increment the accumulator or the index register, and decrement the same thing, you just subtract 1 from either the accumulator or the index register. So our compare and conditional instructions. First of all, we have compare with the contents of an address. Again, this could be symbolic, so it could be a reference to a value like a variable name, effectively. We've got compare with an immediate value, so you just say compare with, say, 5. Is it a value of 5? That's given within the operand immediately. You've got to compare indirect, so as opposed to the CMP, with the CMI, you have to go to the address to find an address, and that address tells you where the value is that you want to compare with the accumulator. So it's one step further removed. And jump jumps unconditionally to a given address. Again, the address could be symbolic, it could be a label within your assembly language program. We'll come on more to that later. And then jump if equal, so if we've done a compare already, you must do a compare before you try and do a jump equal or a jump negative. So jump equal after a compare, if it was true, the compare, then we'll do the jump, otherwise we don't jump. So that will transfer execution from the current instruction, the jump instruction, to whatever instruction is labeled by that value in the operand. Okay, so it's a symbolic representation of an address. And then jump negative means false, negative in the sense that it's false, not true, as opposed to a negative number. And jump negative in this case again goes to the address given in the operand. So whatever symbolic representation of a line of your program. Then we have input output. So in out, in CIE this works in a slightly different way to some. If you key in a character, it stores the ASCII value of that character in the accumulator. So one single character can be entered and stored within the accumulator as an ASCII value. And outputs the screen the character whose ASCII value is stored in the accumulator. So whatever number is in the accumulator is converted into a character using the ASCII table. And in the questions they would tell you usually what the ASCII values are for different characters, so you know what to do. And then there's the sort of odd one out, which is the end. In other systems it's sometimes called halt or HLT, and that just stops the operation of the program and returns control to the operating system. If you didn't have an end or a halt, then what will happen is the code will just run beyond your program, because it's just going to keep incrementing the program counter and looking for the next location in memory and assume that's going to be an instruction to execute when it's not. So you must end your programs with an end command. Bit manipulation we'll look at in the next part of the course in 4.3. Alright, so quick recap on some of the representations. So ACC obviously means accumulator, IX is the index register. An address could be an absolute address, so it could be the actual location, binary location in memory, or it could be a symbolic label for the address. Hash is used for denary, capital B is used for binary, and ampersand is used for hexadecimal. You can label code, so you just put a label followed by a colon and then the opcode operand that you want to carry out, and that's a way of flagging that line of code so you can jump to it if you want to, or just to help the programmer to understand the structure of the program. You can also do this for data, so you can have a piece of data like the value 0 if you want to be able to use that without actually having to say 0 all the time. Then you can, and if you want to change it as well, you can make that a location in memory by doing what's at the bottom there. Give it a label, that's effectively a variable name, and the data value that it's going to start off at. So here's a very simple assembly language program. You can see the labels there, start and end, and then there's a sequence of instructions. So the first one is LDM, which is load immediate. So we take the actual value given in the operand, which is 0 in this case, and we put that in the accumulator. The second is a compare, and again CMP is a compare immediate, so it's comparing the actual value in the operand, which is dneread 10, with the current contents of the accumulator, which is 0, and they're not equal. And then there's a jump if equal to the end, so if the I equal, it'll jump over and halt the program. You can see the end label at the bottom there. Otherwise, it will add 1 to the current contents of the accumulator. So the accumulator will go from 0 to 1 in the first case. And then it does an unconditional jump to the start label. And that goes back and then does it all again, compares again, and adds 1 and so on until the accumulator is equal to 10, at which case the jump if equal will be true and it will jump to end and halt. So this program also demonstrates the need for a 2-pass assembler. The assembler needs to know where the locations are for these symbolic labels. So when we say jump to the end and jump to the start, it needs to know what location in memory that actually is, so that it can replace the symbolic representation, i.e. the end and the start, with the actual memory address that's needed. So if we were to pass through this once and try and work out what this program did in our assembler, we wouldn't be able to work out the end was further down, or we wouldn't know the address of end until we got there. So in one pass, we don't work out what end is until it's too late. We can't do the jump equal end line. We can't compile that, assemble that until we've got to the end of the program. So that's why we need a 2-pass assembler. The first pass is just going to go through and check all the symbolic references and work out where they actually are, completing a symbol table. And then the second pass, we can actually create the machine code with the correct values in for all the addresses. So as we say, this assembly language needs to be translated machine code. It's being done with an assembler rather than a compiler or interpreter. And you could do it in a 1-pass assembler, but with restrictions. In this case, we're going to need a 2-pass assembler. So pass 1, the assembler scans through the whole program to build a symbol table, recording the address of every label. So start has an address of 0, in this case, end has an address of 5, and so on. And no machine code is generated yet. In part 2, we go through the source code again, but this time, whenever we see a label in an operand, we can look in the symbol table and work out what the correct address location should be, and therefore create the whole machine code. So you may be asked to create a trace table for an assembly language program, and you can be given a program with addresses and labels. So this is what I've done here, giving you addresses down the side. This is where each instruction is in memory. So the first instruction, the LDM #0, is at memory location 100. The compare is at location 101, and so on. So as normal, your program will be loaded in consecutive addresses in memory. And typically, it's going to start at the top and run one instruction after the other unless told otherwise. You can see that some of these instructions have labels, so the start and the end have labels, and we know where those labels occur because the addresses are given as well. So start occurs at 100 and end occurs at 105, and there are no other symbolic references in this program. So the first stage of a 2-pass assembler would be to create a symbol table, and here it is for that program. We have the start, the address has been resolved to 100, and the end, the address is resolved as 105. Now we can start going through the whole program again and use those values when we build our machine code. So here's the machine code or object code version of the program. We need to know a couple of things. We need to know the opcodes for these instructions. So LDM, in this case, we've got it as a 01 operand, sorry, a 01 opcode with an operand of 0. So this was immediate addressing. Remember, actually 0 is going to be used, so they filled in 0 here in the object code. And then the compare, so this is given here the instruction operand, sorry, the instruction opcode again of 02, and the operand is denary 10. So it's been written in like this. Obviously, this would be machine code in the real, sorry, it would be binary in the real machine code, but here we've just written it as denary. And then jump to the end. So the jump, they've put in an instruction opcode of 3, and here we've resolved this symbolic reference by looking at the symbol table and replaced it with 105 instead of the end. Add 1, so the add instruction has been given an opcode of 4 and we're adding 1. And then the jump, so jump is a 5 opcode in this case, and then 100 is our symbolic table representation of start. And then halt. And we don't need any operand for the halt, but it's just filled in with zeros anyway. Alright, so you could use this one for a bit of practice. Here's another program. It's listed with the memory address locations. This is the sort of thing you get in an exam. You'd be given the address locations, you'd be given the program, including some labels. Note here that we've got another symbolic representation, num, which is working like a variable. So down here we can see address 109 in memory. We have that value with a label. So it starts at 0, denary 0, and it's called num. So again, just like you need to put these in symbol tables, start and loop, num would also need to go into the symbolic table, the symbol table. You will always get, remember, in the exam, you'll get the instruction set table that tells you what all the instructions are and their opcodes and everything. So you don't need to remember them all. And then this is the sort of thing you've got to fill in. You can create your symbol table. So we've got 4 different symbolic references to fill in, and you can write in the address, and then you're going to actually create the program as well, so you can fill this in if you want to. The format of this might be a little bit different in exams, but the idea is exactly the same. You've got to be able to work out what these things would be, building on your symbols from the symbol table. So working out the actual addresses for this thing, so you can put in the actual address that you need rather than the symbolic reference. So if you want to pause that there for a little bit and have a go at that problem, and then I can show you a solution on the next slide. Okay, so here's the solution. We've resolved the symbolic references, start, loop, end, and num. These were the addresses we found all those things at. And then we can fill in the rest of this table. So we put our program in. We know all the opcodes from the program. And we've got our operands starting as symbolic, but then we can use our symbol table to replace these things. So num here is going to be replaced with 109. So whatever the opcode were given and the value that we've resolved this to. And we do that for all of the lines of code. Again, the halt doesn't need anything. And these are just example opcode values. Okay, so they don't necessarily match up, but it's just an example. Another thing you may be asked to do is trace an assembly language program. And tracing any program, including assembly ones, means stepping through the code manually and recording what would happen to the data at each stage. So in high-level programs, we normally just track certain variables and see what happens to them. In CIE trace tables, you only write the values in when they change. I don't know if you lose marks for this, but certainly the mark schemes never show the values if they're not changing. So it's a waste of time putting them in over and over again if they're not changing. So save yourself some time and don't write them in. And the purpose of tracing programs is to see if they would work before you even try them, or finding bugs in them if you are running them. So we want to step through the program line at a time, instruction at a time in this case, and see what would happen, what would change in terms of the data, and where would it go next. So we're going to look at the format of the trace table in a moment. You'll be given the program instructions and the data with memory addresses. And then you've got to fill in the instruction address with the address of the instruction that you think is going to be running at that point in time, at that step, and any values that change. Okay, so here's an example of a program listing that you might be given. So note that on the left you've got the memory address locations of all the instructions, including the first one. So it doesn't have to start at address 0. It could be anywhere in memory that this program starts. So make note of that and be very careful that you're not assuming it starts at 0. You'll be told what memory contains, if anything, at the beginning. So these memory locations already have something in them. And you may be given some extra information like ASCII lookup values to help you if that's involved in the problem. And this is the sort of table you've got to fill in. So first of all, you're going to be filling in the address of the instruction you think will be running. Obviously, in this case, it's going to start with the very first instruction. It's got no choice because the default is sequence, program construct sequence, if you know about that. So we're going to start with whatever is at address 30 because that's the first part of our program, which is the LDR. So that's going to be the first thing. So we know where we're starting. We write down the address location of the first instruction, and then we see, does anything change in that instruction when that instruction executes? And if it does, we write it down into one of these columns, the accumulator, the index register, or one of these memory locations. And we write in anything that we think would be output at that line of code. So you keep doing that, you keep stepping through the program, working out what instruction would be executing. If you think there's a jump, obviously the next one's going to change. So if this was a jump on this line and you think it did do the jump, then this one would not be the next sequential instruction. It would be wherever the jump label took you to. And then you go all the way through, and typically in a CIE exam question, you'll probably end up at some point outputting a value near the bottom, but it's unlikely to be output near the beginning. As I say, just step through the program, only enter values when they change, only output something when it actually does output a value, and then you should be okay. Don't leave any gaps in the table, and if you make a mistake, just cross out the whole part of the table and start again, but make sure the sequence is still right. Okay, so here's what a completed table might look like. You can see we've put in the instruction addresses of the instructions that we think are going in sequence, and then we've put in values where things change. So the accumulator changes here to 50, and then 52, back to 50, and then 69 on those instructions. In the other ones, we've left it blank because they don't change. Same for IX, it's 0 all the way through here until it becomes 1, and then it stays as 1, and so on. And then we only get the output down here when we do line 41. Alright, in our instructions we have various addressing modes, as you've seen from some of the different transaction, transaction addressing modes. So we've got the accumulator, the index register, or one of these memory locations. And we write in anything that we think would be output at that line of code. So if this was a jump, obviously the next one's going to change. So formats, the immediate ones, the direct and indirect ones. We have various ways of doing it. These are called the addressing modes, and there are 5 that CIE list. They are immediate, direct, indirect, indexed, and relative. So let's look at these. Where the operand, where the opcode goes, typically you'd have part of that as the addressing mode. CIE instructions don't actually do that. They don't reference that. They have slightly different ways of indicating what the addressing mode will be, based partly on syntax and partly by having different instruction names. But typically it is part of the opcode where you have the addressing mode. Anyway, our addressing modes for CIE are immediate, direct, indirect, index, and relative. And you can see what they look like. Typically, immediate, you actually just have the value straight away, in this case a denary value. Direct is you're given an address and you go there. Indirect is you get given an address of an address, so you have to use the address to find an address. At that address you find the value that you want to go to. Indexed, you take the address you were given and that's added to whatever in the index register at that moment in time. And then relative, which I don't think they actually use in the assembly instructions that they give, is an offset from the program counter. Okay, so obviously not PC, not personal computer, but from the program counter. So your program will be executing, the program counter will be storing the address of the next instruction, and relative would be so far ahead from the program counter. As I say, I don't think they use that one in the actual code and programs, exam questions they give, but it is listed as an addressing mode that you need to know. So just recap again, immediate. So the operand is the value, it contains the value immediately, you don't need to go anywhere. Direct, the operand is an address, you go straight to that address and then you read the data at that address. Indirect, the operand is an address that holds another address. So you use the address you're given to go to another address, and then in that address you will go and get the value. So that gives you where the value is. Indexed is whatever address you're given plus whatever contents there are at the time in the index register. And then relative offset from the program counter. Okay, and that is section 4.2 assembly language for CIE 9618.